morning, good afternoon, or good evening, everybody. Welcome back to Unit 6, Energy. Yesterday, we talked about energy and work, and if you don't remember what we talked about yesterday, it would be a good idea to go back and review that lesson. Today, we're going to move into Lesson 6.2, which is all about power. So what is power? Well, as it turns out, power is just the rate at which work is done. Remember, work is force times displacement. If you take work and divide it by time, then you have power. So power is a measure of how quickly you're doing your work. So if power is work divided by time, or force times displacement divided by time, you can abbreviate it W over T, or F times delta X divided by T. There are several ways we can express the units for power. The SI unit is kilograms times meters squared per second cubed. Okay, so this looks familiar. This looks similar to the unit for work, which remember was kilograms times meters squared per second squared. And now we're just dividing work by time, so we've got another second in the denominator there, so it's seconds cubed now. We could also say that power is equal to Newton meters divided by seconds. You remember that a Newton meter is also an acceptable unit for work or energy. And you could also say that power is equal to joules per second, because a Newton and a joule are the same thing. Now, power also has its own special unit. It's called a watt, W-A-T-T. Put too many T's there. And this is abbreviated capital W. And this can be really confusing because work is also abbreviated capital W. So if you see a capital W, how do you know if it stands for work or watts? Well, you just look at where that W is. If it's after a number, then it probably stands for watts. So for example, if you buy a pack of light bulbs and it says 60W, then that W stands for watts. If you see it in the beginning of a formula, like W equals F times delta X, then it probably stands for work. So let's take a look at our very first skill practice question. A crane lifts a load weighing 1.50 times 10 to the third newtons to a height of 55.0 meters in 115 seconds. There's a lot of ones and fives in that problem. How much power did the crane develop? Right, well, looking at the formula for power, it is force times displacement all divided by time. And we have all of this information, so this is really just a plug and jug problem. The force is the amount of force that's needed to lift the load, which would be equal to the object's weight. So for F, we will substitute in 1.50 times 10 to the third newtons. The delta X is how far the weight was lifted, and that's going to be 55.00 meters, or 55.0 meters, just 10, not 2. And then the amount of time is 115 seconds. So that's all, that's it. You just punch that into your trusty calculator, you round your answer down to 3 significant figures, and the answer is going to be 717 watts. Or you could put 717 joules per second, 717 Newton meters per second, 717 kilograms times meters squared per second cubed. Whatever you feel best doing. All right, in this problem, we have 1 horsepower is defined as 745.7 watts. So how much work can a 165 horsepower engine do in 20.0 seconds? All right, so the first thing we want to do is change 165 horsepower into watts. So we'll do a little dimensional analysis there. We'll start with 165 HP, which is the abbreviation for horsepower. And then we will multiply that by our unit factor, put HP in the bottom here, and we'll put watts on top. And according to the problem, 1 horsepower is equal to 745.7 watts. So you multiply that in your calculator, horsepower is going to cancel out, left with watts. 165 times 745.7, rounded to 3 significant figures, is 1.23 times 10 to the 5th watts. So it's about 123,000 watts. I'm putting a rectangle around it. It's not my final answer, but that's okay. Now, how much work? All right, so we're going to use the formula for power. Power is equal to work divided by time. We know the power is 1.23 times 10 to the 5th watts. The amount of work is what we're trying to solve for. So there we got those two capital W's, but here it's a unit and here it's a quantity. And then the time is 20.0 seconds. So hopefully you can see we're just going to multiply both sides by 20. And the amount of work is going to be equal to 2.46 times 10 to the 6 joules. Round it to three significant figures. So about 2.46 million joules, or you could also say 2.46 megajoules if you wanted to. Let's go back and look at the formula for power again. Power is equal to force times displacement divided by time. Well, you see that this formula contains displacement divided by time, which hopefully you remember is the formula for velocity. So we can actually just factor that out and replace it by velocity, and we get power is equal to force times velocity. If you're using a force to move something at a constant velocity, you can multiply the force by the velocity, and that will tell you how much power you're using to move that object. Okay, here we have that the coefficient of kinetic friction between a 2.5 kilogram cardboard box and a tabletop is 0.20. Remember, coefficient of friction does not have units. How much power is developed while pushing the box horizontally at a constant velocity of positive 4.00 meters per second? All right, well, the first thing we want to do is to figure out how much force is needed to cause this to happen. And because the box is moving at a constant velocity, then the amount of force must be equal to the amount of friction. And if you remember from way back in Unit 4, friction is given as the coefficient of friction multiplied by mass times gravity times cosine theta, where theta is the angle of inclination of the surface that the box is sliding over. Well, in this case, the tabletop appears to be horizontal, so theta is going to be equal to 0, which means cosine of theta is equal to 1. So that's not going to affect this problem at all. We can go ahead and get rid of that. So we're left with mu times mass times gravity. All right, so we know that the power developed is equal to the force applied times the velocity. And we know the force is equal to mu times mass times gravity. So we can substitute in power is equal to mu times mass times gravity times velocity. Now we start substituting in numbers. So we've got 0.20 for mu. Mass of the box, we have 2.5 kilograms. We assume this is all happening on planet Earth. So gravity is going to be equal to 9.81 meters per second squared, and the stated velocity is 4.00 meters per second. So really all you have to do is grab your trusty calculator and multiply those four numbers together. And the answer that you come up with, you round it to two significant figures, is 20 watts. Calculator gives you 19.62. We're going to round it down to 2 sig figs because the coefficient of friction and the mass both have two significant figures. And we get 20 watts. So that's going to be it for our lesson on power. I thank you very much for your time and attention. Hope you're having a great day. Hope you'll continue to stay safe. Keep washing your hands. As always, check in Google Classroom. There'll be a document for you to answer some quick questions. And come back tomorrow when we'll be checking in with lesson 6.3, which is all about mechanical energy. Take care. Talk to you later. Bye.